event. Selim is going to tell us about the HGS General Dinner, that's us, predicting deep water geopressures, and the formal title, the Deep Water Geopressure Tolerance Window, Walking a Fine Line, Case Histories from the Gulf of Mexico. Salim has with over 35 years in the oil industry, and he started his career in Egypt as well site stratigrapher and structural geologist. During his last 30 years of service, his main function as exploration geologist was prospects generation in offshore and onshore Gulf of Mexico. Internationally, he also evaluated several exploration projects in Northwest Australia, Libya, Algeria, North Sea, and China. He established GAS to focus on evaluating the implications of geopressure compartmentalization, seal integrity, and salt interactions on leads and prospects worldwide. Pre- and post-drilling risk assessment of a prospect is his specialty. He started these studies in geopressure in the Gulf of Mexico starting in 1984. I remember those times. There wasn't much available except maybe shale density and maybe some sonic information. We've advanced a great deal from there, and here is Selim to tell us about that.
Thank you, Dr. Cassidy, and thank you all of you here. I know it's a pretty day outside, and Columbus Day. Probably got some kids in the school is out today. Was raining yesterday. Good happy days. Anyway, they will tape me today. Are you still taping already? You start already?
It's running.
Can you start now? Okay. Can you hear me? And it's a pretty cozy room, and we are pretty tight each other. And thank you for most of you. I mean, I know maybe 50% of you, and probably some of you are interested in this presentation. So you hardcore pore pressure analysts, and I satisfy your desire, hopefully. In the deep water nowadays, there is some troubles. Is it good?
You're good.
Some troubles. Sometimes you have a great prospect. Four-way closure, beautiful, but you can't reach it. And I show you an example. Halfway, and the borehole was abandoned. And like the last year, when some of the good discoveries in the Gulf of Mexico and turned to a disaster. I consider it as a good discovery because they found oil in an area, gas-prone area in the Mississippi Canyon. If you look at the map, mostly gas, but this is BP discovery was oil. And we need oil. So that's what the presentation is going to cover. Some of the challenges we see in the deep water. Since the 25 slides, coming up slides, are going to talk about pressure, I'm going to give you a little clue about what the pore pressure plot looks like and what it represents. Here is the lithology, the rocks, sand, shale, sand, shale. To build up the pore pressure in the subsurface, we need rocks, fluid, and stress. Here's the rocks, here's the fluids, this is the formation fluids. Here's the stress. We need rocks, fluid, and stress. The stress will build up the pore pressure in the subsurface, exactly like human beings. Stress build up the blood pressure up. And between the hydrostatic and the principal stress is the pore pressure. Any pore pressure profile should be displayed in two parts. part predicted in the shale and the part, the measurable one, not measurable, measurable. The one you can measure is in the sand, right there. You see how the pore pressure profile progressed from the top to the bottom. If the pore pressure reach a point where they exceed the limit and start fracking the formation, this is the frac pressure. So we have the lithology, hydrostatic, pore pressure in the shale, pore pressure in the sand, and the frac pressure and the principal stress. That's what you're going to see in the next 25 slides. So remember this term. Here is what I refer to the drilling tolerance window. I'm going to call it the window from now because I can't say drilling tolerance window all the time. So the window, let's call it the window. Am I in your way? Okay. Here's the lithology, hydrostatic, pore pressure, frac pressure. This window between the pore pressure and the frac pressure, this window is very important. This window dictates how deep it can go, what your mud program looks like, and how many casing points you need to drill to reach your objective. So we use the mud to drill anywhere, right? The function of the mud earlier we used to say just remove the cutting and lubricate the drill bit. But the mud has a very essential function, is to keep the sand bed from flowing to the borehole and to keep the shale bed from breaking out. What do you call it? The borehole integrity. You cannot drill or use mud weight very close to the frac pressure, and here comes the safety issue, the safety limits. So we're getting a little complicated here. You got the pore pressure, you got the frac pressure, you got the mud weight in between, and you have a safety limit. So it's getting a little bit complicated. Let's go through and see some examples now. What happened when you, for that window, when you go from shallow water to deep water? What will happen? Here is your gas gradient, oil gradient, the water formation gradient. Here is the principal stress. We're going to assume they're a cross with 20,000 feet in both of them. We're taking the mud weight 7,000 feet down, and let's see what happened to the principal stress. That principal stress, or the rocks, is going to move down 7,000 feet. Therefore, your principal stress moved 7,000 feet, your pore pressure moved down 7,000 feet, and of course the top of the dew pressure, and your frac pressure follows suit. Look at the difference between this window and this window. In the deep water, the window here is relatively narrow, or maybe 30 or 40% narrow compared to the shallow water. Therefore, you need 3 casing points here to reach your objective at 20,000 feet, and here you need 4 casing points to reach your objective. That's the difference. Also, have you noticed nowadays in the deep water they found more oil than gas? All the new discoveries in the deep water, you see a lot of oil. The reason is, if you look at the gas and oil gradient here, and we superimpose that gradient here on the deep water profile, you can see you can trap more oil than gas because the gas have high gradient, because this is a narrow window here. If in the shelf we can trap both of them without any problem. Here's an example of transgression and regression. We were talking about transgression and regression, Mark. We were talking about transgression and regression. Let's read an example from vast canal prospect. And this is the pressure RFTs were taken from 10,000 feet to 13,000 feet. Within 3,000 feet, you have regression, transgression, very strong transgression, and an regression again. What is the reason for that? So a lot of people have a lot of guessing gains here, or not gains, examples. The mud pressure here is, we're going to assume this is the mud pressure to drill that well. When you have a transgression here, you might have a kick and can lead to a blowout. On the other hand, when you have a regression, you can lose circulation. This is one of the problems of transgression and regression. And transgression and regression mainly due to structural impact. This is a well has been drilled in offshore Texas about 9 years ago. And from the velocity, the seismic velocity, this is what pore pressure looks like. And also from the seismic, we calculate the overburden or the principal stress. In between, we have the frag pressure. And we have the coefficient for it, and we did it. So we drilled this well, or they drilled this well, up to here. It is the mud weight. Now this is the mud weight here. Here is 2 leak-off tests. The leak-off test means frag pressure. You measure the frag pressure in that formation. And based on the frag pressure up here, we calibrate the frag pressure way ahead of the drill bit. So the calibration was good. So the mud weight is supposed to follow the pore pressure down there. But unfortunately, the tool pusher and probably the people dictate how this is going to process to reach this point, reach the next casing point. Let the mud weight go straight. Didn't change. It doesn't follow the pore pressure. What happened? There are a very small streak of sand. It's about 10 feet. And the well start flowing. They kill the well, and the formation break down. This is the cycle that's very common in the deep water. Flow, kill, and break down. This cycle took about a year to try to heal that well, or to fix that well. It didn't work out because with the well flow and you kill it, when you kill it, you start losing circulation because you increase the mud weight, so you start losing circulation, and you reduce your mud weight, you go up again, try to drill, you raise the mud weight. This is kind of like an endless cycle. So after a month, to pass that 5 feet of sand, the well was dry and abandoned, or plugged and abandoned, not dry and abandoned. Let's see how that, if you have a discovery or a gas column or hydrocarbon column, how this is going to impact your window. This Mississippi Canyon Block 296, and this block is south of Maconda Prospect. And I might just sit down. Everybody can see? All right. Look at that pore pressure profile here. This is the mud weight. That's an indication of pore pressure. Here is the RFT, measured pore pressure. Here is the leak-off test. Look how narrow this window is. You cannot maneuver. It's pretty tight. And it took about 7 casing points to drill 10,000 feet. So every 1,400 feet you're going to stop at casing point because that narrow window. Let's take this piece here and enlarge it. Here is your water gas contact. Here is a gas column. Here is the mud. It is the leak-off test. That's the frag pressure, and that's the window. The window without the gas is going to extend up to here. But because the gas column, so your window shrunk. And when the window shrank, the ability to maneuver with the mud weight is very restricted. So that's one of the problems. If you have a prospect tube, and you have to get ready for how thick the hydrocarbon column is going to be. This is block 252. And Texaco drilled that well about 10 years ago. I don't know, the same location of Macondo or not, but in the same block. And look at that narrow window. Need 6 casing points to drill about 6 to 12, 6,000 feet. So every 1,000 feet you're going to set casing point. That's expensive. So here's Macondo. All this information is in public domain. I don't get anything from anybody. And just my interpretation has nothing to do with the Macondo prospect. Here is the mud weight. I mean, not the prospect, the investigation. Here is the mud weight. Here is your leak-off test. This is published information. And here is your window. It's about 1.5 pounds. So you're going to maneuver very easy. So what happened here? You got 8 casing points to drill from 5,000 feet to about 17,000 feet. And here's the discovery turned to a disaster. That hydrocarbon column make that window very narrow. And I have no idea what happened, but from the mud weight, I can tell that they reduced the mud weight at the bottom of the hole, so there is a problem, a loss of circulation at the bottom of the hole. Indication, have no information. So the hydrocarbon column or that discovery turned to a disaster because of the presence of the hydrocarbon. Now we're going to move to another area. We go into the 6B escarpment. And I'm going to go through 2 prospects in the Wilcox and another 2 prospects in the New G. Here's the salt toe. It looks like a toe, right? Looks like a toe, but I don't know. You have a fungus nail or something. Here is that, from this side of McLean here, you can look at it, you see there is a structure. It's very rare you find a good structure here in the Gulf of Mexico. 4-way, nice. What happened here? The salt was moving down there, and the principal stress became horizontal or lateral. And I do believe this buckling, sediments buckled during the sedimentation of this package here. And then the movement has been ceased. And then start again. So the movement of the salt is just like events, and cease and events again. Create that thrust fault, and the geomechanic of this part looks like this. Your principal stress is going to equal to the tectonic force. So it's coming sideways, and your overburden becomes the minimum stress. So if you frac your pressure, or you run a leak-off test, and the frac pressure is going to be equivalent almost to the overburden. And you see that a lot. Share some examples. Okay, here's the model, the geopressure model. Here is the Wilcox, sitting there for 40 million years or 50 million years, mind their business. And, you know, usually the pressure decays with time. So probably the pore pressure was the top of the geopressure here and decay with time. Aging, you know, you age, you decay. So, like me. And here's the salt. Come shoving in, down depth, pushed by sediments, and breaking with two things. Rafted blocks or rafted sediments, and plowing the bottom of, or the contact between the salt and the sediments. So, what is going to happen here is the principal stress. Above the salt, the principal stress higher than the overburden. Below the salt, less. Here's your pore pressure, here's the frag pressure, follow the pore pressure, and watch the pore pressure here. It's got a little bit of strong regression here. That area is being plowed down by the salt and the sediments. It has a lot of shear to it, and lost the pore pressure in it, and reached the frag pressure easily. So this zone, it caused a lot of troubles drilling along that trend, which is 6B trend. I'll show you an example here. There are two wells. One in St. Malo, and this is Jack 1 and Jack 2. This is St. Malo. They were drilled by Chevron. Can you see? All right. Okay, I'm uncomfortable looking at it this way. I wanna, huh? Can I come here? Sit down? Think so? All right. So here's two wells. One is Jack, one St. Malo, or St. Malo. And here that looks like on the seismic line. If you look at the seismic line here, you see a little bit of streaks. This is the overlay of the well log on the seismic here. Very high resistivity in some pockets here. Okay, what happened to Jack? Mr. Jack here is the overburden. This is calculated from the weight of the sediment, just density, right? And I'm going to use the mud weight as a pore pressure indicator. Here it is. Then here's the leak-off tests. You notice here when I said, okay, the frag pressure is almost or above the overburden. Here's the frag pressure outside the overburden. Above the salt. Below the salt comes the back. Here's the calculated frag pressure, and look at this. Here's your pore pressure, or the mud you drill the well with. Here is the frag pressure. They meet at that point in the gouge zone where the salt plow the sea floor. And why is that? Because it was a dirty salt. The dirty salt, the clean salt is supposed to have no pressure because it's solid. It doesn't have permeability, it doesn't have porosity, it doesn't have fluid. And, but here, you see the pore pressure increase. This is due to the inclusions of dairy salt. Also, here is the RFTs, and this is a little bit of calibration problem here. You see that? Turn it off. You see that RFT? Usually we have a problem when we convert RFT from PSI to PPG, give you a reverse inclination or trend. Tom. Okay, here's the mud log. The mud log and jack. The jack in the middle, you got a lot of inclusions here. And at the bottom of the salt, there's no mud return. They lost mud and they sidetrack, and they saved it. On the other hand, next to Jack, about 10 miles, there's St. Malo. St. Malo, here is overburden, here is the frac pressure, as usual. The frac pressure here is higher, below the salt is lower, and here is the mud weight. I use it as a pore pressure profile. Over here went from the top of the salt to the bottom, go through the gouge zone without a hitch. Went straight, no problem. Why? Because the window, the DTW window was wireless. I mean, the driller can play around, he can increase the mud, he can decrease the mud, there's no problem. Because it was clean salt. No salt inclusion, no rafting blocks. And need about 3 casing points to reach the objectives. So, now we have two wells, Jack and Malo, or Malo. One was a very, very narrow window, where one was wide window. The reason is, this one was in a dirty salt, drilled in a dirty salt. This was drilled in a clean salt. We have another example also. Repeat the same case, or the same thing. Atlantis, that's drilled about 12 years ago. Here's the overburden, calculated from the density log. Here is your mud pressure, represented the overburden, represented the pore pressure. And you see here the pore pressure increased within the drilling through the salt. You're not supposed to. And they lost circulation in the salt. Then I put casing in the salt. You're not supposed to casing in the salt if you don't have any problem, right? So the frac pressure going increase this way above the overburden, and then becomes back in the gouge zone or the plow zone and become less than the overburden. Look at the drilling tolerance window is very narrow, and they suffer a lot of troubles. The flow, kill, and breakdown cycle, the cycle I mentioned before, because it was a dirty salt. So actually the dirty applied to troublesome. You know, if you have a dirty salt, you got a lot of troubles. Here is Exxon. About 3 months ago, they announced their discovery of Hadrian, Keithley Canyon 919 #1. And I plot everything here. It is the mud weight, represent pore pressure. Here is the frac pressure below the salt. We assume that frac pressure above the salt is going to be above the overburden, below the salt is going to be less than the overburden. Look at that drilling tolerance window. Nice, because this well has no trouble whatsoever. And here's your RFTs with that reverse slope. By the way, we fixed that reverse slope. So here is your clean sand, clean salt, I'm sorry. Here's your Exxon discovery. So the correlation between, even in the Pliocene and the Pliocene, the Neogene, you will see the same thing. If you have a dirty salt, you will have a trouble, especially in the gouge zone. If you have a clean salt, your drilling tolerance window is wide, and there's no problem whatsoever. Okay. Here what I was talking about, integrating the geology to the pore pressure prediction. Here is a ramp And we will assume there's sand, 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 and shale. So, number 2 and 4, they are in communication, right there. Communication here, right there. Okay. Number 3, encased inside the shale, shows being completely sealed. What would happen here? I bring the velocity and I take it to some pore pressure analyst, put it in the software, and come up with this profile. This is my pore pressure profile. But, and I'm gonna design a mud program, okay, maybe about a pound or half a pound, it depends on your liability, for this well. I haven't drilled the well yet. But I'm going to talk to the geologists and geophysicists. Can you tell me where is the trouble points? Where we're going to see some troubles here? Say, well, those 2 layers here in communication. So what are we going to see? We're going to see the pore pressure on those 2 layers here, number 2 and 4, sitting in the same pressure envelope. It's not a window now, it's an envelope. This one, the encased one, completely sealed, is going to be in a higher window. So I expect what I'm going to see here, I'm going to see a pressure transgression here. Since I drill through that shale, go to the sand, I'm going to see the same thing I saw. Remember that well as a flow Kelvin breakdown? That's exactly that's what I'm going to see. On the other hand, over here, I might see a loss of circulation because the mud weight, the predicted mud weight, and the actual pore pressure in the sand is a big window between the mud weight and the actual pore pressure. So this is very important to do sequence stratigraphy, structure. All the geological work goes hand in hand with prospect generation. I mean, it has to be. It's not at the end. You know, hey, here's my velocity, give me the pore pressure. You gotta incorporate geology with all disciplines to find your the most troublesome zone is the interface between the seal and the reservoir. You drift through the seal, even if the mud weight less than the pore pressure in the shale, and you might have some trouble with the borehole, widening borehole, and but it's not going to harm you. It's going to harm when you step out of that shale going to the sand. So let's go to the conclusions. Is that enough or more? Okay, pore pressure predicted in the seals and measurable in the sand. We know all of that, right? Okay. You can't predict the pore pressure with the velocity in the sand or the reservoirs. Also, the drilling tolerance window is dictates feasible prospect drilling programs. What is the factor to reduce the drilling tolerance window? Let's see what it is. Water depth. The larger the water depth, the narrower your window is. Okay. That's why when step from the shelf go into the flexure trend, we didn't have that problems because the water depth was 2,000 feet, 3,000 feet. When we go to 5,000 feet and higher, that drilling window that becomes very narrow. So also, transgression and regression cause a lot of troubles, and we need to find out where the transgression is going to take place, where the regression is going to take place from go back to geology and geophysics and pore pressure analysis. Hydrocarbon column, reduce that window. So if you're drilling a prospect and you tell your boss, I got 300 feet of gas here, you better be prepared for it when you drill that well, because that 300 feet of gas is going to reduce that window. And you're not drilling for a dry hole, you're drilling for oil and gas, right? Dirty salt always reduce the DTW, always. The most troublesome spot along the borehole trajectory is the sea reservoir interface. The sea is no problem. The reservoir is going to flow on you. Establishing geological building blocks for pore pressure prediction goes hand in hand with prospect generation and forecast drilling challenges. Borehole instability, bypass, sidetracks, flow kill breakdown cycles, partial blowout, and failure to reach that prospective target are common in deep water due to the narrow DTW. Oil versus gas. We find a lot of oil in the deep water because the narrow window. So that narrow window play double sword edge, or double-edged sword, I'm sorry. Because it doesn't have enough sealing capacity to hold the gas, but it's to hold the oil, because the gradient is different. Thank you. I thought it was going to be 25 minutes, right?
Very good, very good.
Thank you, sir.
Now there's time for questions.
Yes.
Any questions for the speaker?
Can we have the last slide? Can we have the last
Back up.
Last slide, yes, sir.
slide?
I can leave that last slide. Okay. Hit.
You showed a lot of subsalt geology, and you always showed the gouge zone. More or less, I mean, as a rule of thumb about how thick this gouge zone is below the salt, and the subsalt exit.
How thick is that?
The gouge zone.
The gouge zone. Here's the problem with the gouge zone. If they lose circulation in the gouge zone, forget it. You can't get any samples. You can't predict. I mean, how you see it. You're going to go through it and fast as you can. After you heal the well, right? You got to bypass or sidetrack. But it range from, I see it in mudlogs sometimes, range from 100 feet, 50 feet, 25 feet. This plowing is not even. You're not putting it even. Right? It's just some areas thick, some areas thin. It depends where the feeder system. You know, the sediment's feeder system pushing down. But I can't give you a number.
Not like you're out of the woods when you're 200 feet past it, you think?
Out of the wood, I don't know, but Mark, this is hard question for the geologist. I would say range from 5 feet to 300 feet. No, 300 a lot for a gouge zone, maybe 200. 50, 200, maximum 200. And this is one of the costs $100 million sometimes. It costs Chevron for Jack maybe about 20 million to just bypass that zone. Yes, sir. Yeah, whatever.
Yeah,
Yes.
just to follow up that a little bit, where would you set casing then, in the case of a dirty gouge zone?
The dirty salt?
Yeah. Where would you ideally want to set casing?
Well, ideally, I'd set casing above the salt, and if it's clean salt, you'll be lucky. You go through without setting casing, and pass that gouge zone and sit casing.
So it'd be a short string then? After the casing in the salt, it'd be a short casing string?
Well,
So if it's dirty salt, do you set it in the salt, get through the gap zone, and then set a short piece of casing?
No, no, you have to the whole casing from the top to the bottom. Now we create another problem, because you have to put a short one out. But, yes, sir.
Yeah, you mentioned a dirty and a clean salt. Is there a compositional difference between the dirty salt? Like, is it attacking the hydride compared to the clean salt?
Well, the dirty salt, what I meant dirty is nothing, is not the inclusion inside the salt like sand, shale sand. No. It's rafted block. Sediments come with the salt itself. Like in the mud log, can I go back? Sir, can I go back? Okay. In the mud log, you can see that it's like 20 feet or, let me see.
You pass through one side.
No, that's not a mud log. Right there. See, this zone here is about maybe it's about 30, 40 feet of sediments within the salt itself. It's like sandwich in the salt. It's not embedded in and sandwich. Big blocks. Like 20 feet here, there's 10 feet here. And here is the gouge zone. No return. That's the only explanation of the mud log. And you can't get any sample. You have to bypass quick. Yes, sir? I hear some whisper here. Yes, sir?
Can you explain how the pressure gradient can be higher than the overburden pressure?
You know what? I wish I have that presentation in the back there over here, but I can explain it. And if you have a sediments, salt and sediments, okay? The salt in between has less density, right? So the salt tries to float up. On the top of the salt, or the sediments on the top of the salt, you get two forces. One, the overburden, and the other one is the buoyancy, or the salt buoyancy, right? So in this case, the overburden is the calculated overburden, okay? The density overburden is not the principal stress, because you have two stresses. One is overburden, which we put it in our calculation, and another force coming from down, which is the salt buoyancy. This is not calculated in the overburden. You want me to go to the slide? Huh? I see you shaking your head. You want to go to the slide or not? Okay, here it is. All right. Now, all right, here we put the salt, inject the salt in the formations. Okay, here is the salt buoyancy, right? Here is the principal stress. Because the principal change. It's not the weight of the sediments the principal stress anymore. You agree?
So with principal stress, you mean the maximum?
The maximum stress. See, the maximum stress is sideways down because it does buckle or lift the sediments up. So this one, or the overburden, becomes probably the minimum stress. And this is the principal stress. So the salt buoyancy and the overburden, they act against each other, or they add to each other to squeeze the sediments harder and faster. That's why if you have a normal compaction trend, the trend here is going to be, the slope is going to be a little bit steep.
I don't understand.
Huh?
I don't understand that because the mud line is free to move upward. There's nothing constraining it.
No, I'm talking about the sediments, not the mud line, sir.
But the whole sediment column will,
You have two forces.
salt in the sediment column will be moving up. So the buoyancy of the salt doesn't count because there's a free surface at the mud line, so the whole.
Yeah, but you have two forces, the buoyancy here. Do you agree this is 2.2, that specific gravity? Here is 2.2, here is 2.1 or 1.2, 1.9, right? So this is try to escape, try to go up.
That's right.
All of the salt try to go up. So you have two forces, the buoyancy of the salt and the weight of the sediments. So in this section, from this point down to this point, you have two forces. It's not just one. It's not just the overburden. Yeah?
I think we might leave
We can, no, you can, I mean, I got all time you want. I got a display there if you want to look at it.
Actually, some of these now can be discussed offline.
That's right.
Are there any general?
Offline.
Offline.
That's a good idea.
Any general questions? Well, thank you very much. It's been
You're welcome, sir, very much.